All right, take it away.
Let's see. So first, I'll begin by introducing you to how we're utilizing UAVs within our breeding program, some of the phenotypic traits that we're interested in evaluating with UAVs. And then I'm going to compare the different methods of manual measurement, visual ratings with UAV-based estimation using correlations and rank comparisons, and then share with you some of the next steps and how I would like to apply this moving forward. And like Jeff said, Richard, thank you for doing such a beautiful job introducing UAV-based phenotyping. It really, you did a great job, and I appreciate that. First, I want to acknowledge the collaboration of Dr. Jing Zhang in this project. She did all the imagery and image analysis for this project. She works in the turfgrass breeding program here in Tifton, and we're really grateful for her lending her expertise to this project. So Richard already described a lot of the interest for using UAVs and phenotyping for breeding. Some of those include, because it's very rapid, potentially more accurate than what we can do from the ground. It's convenient. Once you image a field, you have a permanent record that you can go back and reanalyze as methodologies improve. But the thing that really excites me about the potential for UAV-based phenotyping and high throughput phenotyping is the scaling potential. As a plant breeder, we only have time in the day to look at a couple hundred plots or a few hundred plots. Whereas if you're collecting data by way of drone or some other high throughput method, you could potentially be evaluating thousands of plots. And that all influences our genetic gain or potential genetic gain. If we're increasing our accuracy of measurement, we increase our heritability. And then because of the scaling potential, we can also increase our selection intensity and our population variance because we're looking at a lot more plots, a lot more progenies, even more crosses. So a lot of potential for increasing our rates of genetic gain there. So one of the first traits that we took a look at was plant height. Jing had a lot of experience looking at turfgrass and other row crops for plant height using UAVs. So we started that in 2019. Maria Belota's group, they've done a ton of work using UAVs, and they beat us to the punch there with Scienton's paper in 2020. But he was looking at the mini-core collection and measuring peanut canopy height using UAVs. And we wanted to try and replicate their success, but on a more narrow set of genotypes, in this case, UGA runner cultivars. We're also looking at stand establishment and seedling vigor. These are very important traits for growers. Replant situations are time and profit consuming. And then vigorous seed and seedlings ensure uniform stands, resilience to poor weather conditions, and it also helps to get peanuts out of that early season susceptibility period to early season stresses. We're also looking at mid-season plant vigor, which is just a measure of speed of canopy closure or lapping, as it's commonly called. Closed canopies preserve soil moisture, it shades out weeds, and it's really a relief for a grower and a milestone during the growing season. So our overarching objective here is to see if UAVs can be used to collect actionable data for cultivar improvement specifically. The experiment I chose to validate these methods on it's a genetic gain study I've had running for a few years now. We're getting ready to publish the results of that study, but it contains 16 runner cultivars released by the University of Georgia, the first of which is Southeast Runner 5615, which is UGA's first runner cultivar released in 1937. The second is Georgia Runner, which is Dr. Branch's first runner cultivar, and then almost all of the runner cultivars that he's released since then, up to Georgia 18RU. We've grown this trial in Tifton as an RCBD with 4 reps in 2019, 6 reps in 2020, and 4 reps in 2021. The data we've collected stand ratings for 2 years, seedling vigor ratings for 2 years, plant height at around 45 days after planting for 2 years, mid-season vigor ratings at around 45 days after planting for 3 years, and then plant height at about 90 days after planting for 2 years. The drone we're using is a Phantom 4 equipped with the stock RGB camera. We're using drone deploy for the flight control, Pix40 mapper for image processing, and ArcMap and R for image analysis. We're flying at an altitude of 20 meters with 60 to 70% overlap front and side. For the manual plant height measurement, we're measuring that at the main stem. We're taking 6 measurements per plot, so that's 3 per row, and averaging those numbers to get the plot average main stem height. For the UAV-derived measurement of plant height, it's a measurement of canopy height extrapolated from the digital terrain models, digital surface models, and Jing divided each row into 4 sections, took the max value of canopy height extracted from each of those sections, and then averaged those across the plots. So I'll have a few graphs set up similarly to this one. On the x-axis, we have either the manual measurement or the visual rating. And then on the y-axis, we have the UAV-based estimation for comparison. So this is plant height collected at around 45 days after planting, main stem height on the x-axis, the UAV canopy height on the y-axis, and we have a very high R-squared value of 0.95 across 2 years of data. So I'll have several tables set up similarly to this one. The first column is the cultivar name, followed by the rank for main stem height at around 45 days after planting, then the mean separations, and then ranks for UAV-based height at around 45 days after planting, followed by the mean separations. At the bottom of the tables are the LSDs. These are Waller-Duncan mean separations at K equals 100, and then CVs at the very bottom of the table. So what we see when we compare the ranks for these two measurement methods is that the ranks agree to a large degree. There are some differences for the absolute value. For instance, the UAV canopy height measurement underestimated height at this point in the season. But what's really neat is that we get really good mean separations. We can tell differences that are pretty minute. You know, the shortest cultivar here was 24 centimeters, and the tallest was 31 centimeters. So a difference of 7 centimeters, and we can statistically separate these cultivars based on plant height using UAVs, which is pretty incredible to me. When we look at plant height at around 90 days after planting, we see, again, a pretty high R-squared value of 0.75 across 2 years of data. Comparing ranks, we again see a very similar relationship here. We have the ranks agree largely for both methods. We get good mean separations. The CVs are very low. The CV was actually lower for the UAV-based method of measurement. Absolute values do vary by a few or several centimeters for the UAV-based canopy height. But the main takeaway here is that we can tell relative differences between cultivars for plant height. So looking at plant vigor, you know, I routinely take visual vigor ratings for stand establishment. It's on a 1 to 9 scale, with a 1 being a poor stand, 9 being very good. For seedling vigor, also a 1 to 9 scale, with a 1 being a poor vigor, 9 being high, and then similarly for mid-season vigor, 1 is poor mid-season vigor, and 9 being very high. We compared those visual ratings to percent green cover, which is a measurement of percent plot area that's covered by green pixels, and that's based on a green leaf index threshold of 0.05. So this is our data for stand and seedling vigor. We've got stand on the left here, seedling vigor on the right, and on the y-axis, we've got percent green cover. So in 2020, the R-squared values were pretty low, 0.1 and 0.2, but were statistically significant. And then in 2021, a little bit better R-squared values with 0.3 and 0.2. When we look at the rank comparisons, we see that the UAV-based method looking at percent green cover was sufficient for determining which were the top performing cultivars for stand and which were the lower performing cultivars for stand. However, you know, it's in this middle section here where we get a lot of disagreement for rank comparisons. I'll note here that the CV for percent green cover at this early point in the season was quite high with 34.8. Looking at seedling vigor, we see a very similar relationship. UAV-based method was effective at selecting the top and the low performers, but disagreed with the visual ratings here in the middle. So looking at mid-season vigor across 3 years of data, we get very high R-squared values. We got 0.785 in 2019, 0.86 in 2020, and then 0.75 in 2021. So very, very good correlations between mid-season visual vigor rating and percent green cover. When we compare the ranks, there's a large level of agreement between the ranks or the rankings. Percent green cover actually had a lower CV here than the visual rating system. And we get really good mean separations for both measurements. But it's exciting to see that UAVs can confidently be used for evaluating mid-season vigor. You know, I feel like we've validated this pretty well in our replicated yield trial. And so next, my next step is to validate using these methods of selection in progenies in nurseries. So this year I've got some F3 progeny rows growing in the field. There are crosses between 18RU and TIFGuard and Georgia 18RU with Georgia 14N. And, you know, I took seedling vigor ratings as well as UAV data. We get very good R-squareds, actually better than the yield trial here. And then we see a similar relationship for mid-season plant vigor with R-squareds of 0.6 and 0.55 for these two populations. And so my next step here is to select progeny rows that are high performers for seedling and mid-season vigor and low performers, and see if those hold true in the forward generation. To conclude, plant height was good early season, but more accurate later in the season. Our results really support the findings of Sarkar et al. And really extend them to even genotypes that are very narrow and show less diversity than the mini core collection. Using UAVs to evaluate stand and seedling vigor, it was good at picking the highs and lows, which is probably good enough for picking progeny rows out of nurseries. And then for mid-season plant vigor, the UAV-based estimation was really similar to the visual rating methods. We think UAVs hold a great deal of potential for application within breeding. We saw that in Richard's talk. Maria's group's done a lot of work in this area, and this just further supports and extends these results. And we feel like we're only scratching the surface of potential capabilities using UAVs for plant breeding purposes. I want to quickly acknowledge my co-authors, especially Dr. Branch, my mentor in peanut breeding. I want to acknowledge Dr. Jing Zhang again for her imaging and image analysis, Dr. Valesky, Dr. Schwartz for their help in this project, our farm managers in Tifton and Plains, our peanut breeding team here in Tifton, and then our funding agencies that allow us to conduct this research. All right.
Great, thanks, Nino. I will agree. I think we are just scratching the surface, and I think you can tell based off the number of talks that are on UAV that this is a very exciting and potentially game-changing type technology for at least in breeding, but across the peanut board. We do have a couple of questions real quick. One from Josh Clevenger. Nino, plant height, is that for testing the UAV method, or do you select for a particular plant height?
Yeah, so not very important for cultivar development. The goal here was to see if we could differentiate minute differences. Like you're saying, it was more for validation more than anything. But it's pretty incredible to me that we could tell differences of just 2 or 3 centimeters between cultivars aerially.
Mm-hmm. And then a second question, and this one has always been on my mind, from Albert Culbreth. Have you used imagery or reflectance of inverted plots relative to yield?
So we have a little bit. We haven't had a whole lot of success for various reasons that I won't get into too far. There's some potential there, but I hope to see somebody have better luck than we've had.
Yeah, I'd agree. I think a lot of people are very interested in that, and whether or not, you know, you could use that as a predictive measure in terms of, you know, selection. But, you know, I guess we'll wait to see.
That's right.
Well, thank you, Nino. Appreciate the presentation. We're going to move on to our next presenter.